Hi there, this is another practice problem on the sampling distribution of proportions. So let's see what this context is here. It says information on a packet of seeds claims that the germination rate is 92%. Okay, that's a percentage, so that's our P. There are approximately 160 seeds in each packet. Okay, that's our N because that's think of as a packet of seeds as one sample, okay? Discuss each of the conditions required to use a sampling distribution for the proportion of seeds that will germinate, okay? So the P, what we're measuring is what percentage will sprout. If you like starting seeds, you probably know all about this. Some of them start and some of them don't. Okay, so we need to go over our conditions. One is independence. Okay, what would we need for our seeds to be independent from each other in terms of germination rate? Okay, well, we don't know exactly what kind of seeds these are. Are they flowers? Are they tomatoes? Are they peppers? What kind of seeds are they? But it seems like if all of the seeds came from one particular plant, then they might not be independent of each other. Could have been an extremely good plant, could have been kind of a dud plant, or maybe the seeds won't germinate. So it seems like if the seeds are being collected from lots of different plants or flowers, then they would need to be mixed up really well, okay? So I would say that seeds from different plants should be mixed well, so the seeds are independent in how they germinate, or in germination rate. So I hope that looking at all these different contexts kind of helps give you a feel for how to write out these conditions. So that's independence, and then also 10%, 160 is going to be less than 10% of all seeds produced or packaged. Since they're not really made or produced, they're packaged. So I'm assuming that this is going to be a larger operation, so that 160 is less than 10% of all the seeds, because they're going to be sampling without replacement. Okay, so 2 is, remember what it is? Randomization. Okay, so the seeds must be, oops. Again, it kind of like means they should be mixed up really well, right? So like when you're taking a random sample, if you're packaging, okay, this seeds from this flower in this package, this flower in this package, then again, they wouldn't be randomized, so they wouldn't be independent. So seeds must be well mixed before packaged. Okay, and then our third one is the success failure. Okay, so N times P. Our N is 160. Our P is 0.92. Let's see what that's equal to. 147.2. Don't worry if you get a decimal. That's greater than or equal to 10. Whoops. And our N times Q is 160 That's 92%, so 8% would be the complement. What we need to make up to 100%. 160 times 0.08 is 12.8. Ooh, just barely on that one. Just barely on the success failure condition. So 160, not that huge of a sample size, because remember, this is really high. This is closer to 100%, so this is going to be skewed unless we have a large enough sample size. So, but this looks like we're pretty good. 12.8. We made it. So now we can define the sampling distribution model and its parameters, or its inputs. Okay. So we are talking about p hat for a sample proportion, and because these conditions are met, or as these conditions are met, we can go ahead and do our formulas for the distribution. So our mean is the sample proportion. Here's from the last page. Our population proportion is our mean, so 92%. And then our standard deviation is the square root of PQ divided by N. Square root of 0.92, and what's nice is we've already figured out Q in our success failure, so use that to save you time. Divided by 160, which is N. Okay. Let's go ahead and figure out what this standard deviation is. So we're going to do square root 0.92 times 0.08 divided by 160. 0.0214, and looks like that's going to stay a 4. 0214. That's for technology. But when I draw it, I'm going to do 0.02. Okay. So now we're going to sketch and label the model. So yay, we get to make another normal curve. I'm going to leave myself lots of space to label this one. Okay, our center is 0.92, 1, 2, 3, 1, 2, 3. And this is 2%, so this is a little wider. The other one we had was only 1%. So 92, 94, 96, 98. So what that says is on the high side, some packets might have a 98% germination rate. 90, 88, 86, but on the low side, some packets would have an 86% germination rate. Okay, so this is the proportion of seeds that germinate in samples of 160. Okay, so if you take your whole seed packet, plant it, that's your sample. Okay, so that is our model. Pretty cool, right? Those are all of our random samples that are possible, essentially, if our population proportion is 0.92 and our sample size is 160. Okay, so now we can find our probability. So once you do a couple of these, they're all the same, so you'll have no problem once you get a few under your belt. So the probability that p hat is, what's the probability that more than 95% of the seeds will germinate? P hat greater than 0.95 equals, and now we go to online stat book. Oops, wrong one. Too many windows as usual. So our mean is 0.92. Our standard deviation is 0.0214. And we are looking above again. They won't always be above, but they seem to be, these examples seem to be above. Above 95% is 0.0805. Okay, so, and we could write this out in a sentence. Probability that more than 95% of the seeds will germinate is 0.0805 or 8.05%. Okay. So here's another question, which kind of gets to what we're going to be looking at in the future. Would it be unusual for only 140 or fewer of the 160 seeds to germinate? Explain. Okay, let's think about this. So 140 out of 160. Sometimes instead of giving you a percentage, like right here, they give us a numerator and a denominator. So the first thing we need to do is figure out what percentage would this be, okay? So look for, you'll either be given this information or this information. Sometimes we have to find our p-hat is 140 out of 160. So that's why this example is in here, to show you both situations. 140 divided by 160 is 0.875. Okay, so essentially what this is asking is, what's the probability of getting less than or fewer? What's the probability that p-hat is less than 0.875? Okay, so let's find that out. And we'll see if that seems unusual or not. Oops, I did it again. So our same mean and standard deviation, because we have our same sampling distribution, but this time our p-hat is 0.875. So we want to see how likely that is. And oops, sorry, I want to go below 0.875. Okay, not super likely. Let's see. Oh, only 1%. So is 0.0177. Okay. So that would be, remember, we talk about 2 standard deviations from the mean, beyond that being unusual, and beyond 3 being rare. So this would be unusual because it's over 2 standard deviations away, which also kind of corresponds with less than 5% probability. So this would be unusual. For 140 or fewer, or 87.5% or less to germinate. Now you might have been thinking, oh sorry, wrong window. It would be unusual for 140 or fewer, which is also 87.5% or less, to germinate. You might have been thinking, well, why don't we calculate the z-score? That also tells you how many standard deviations away it is. So let's do that too for fun. The z-score is going to be the value, I won't put it in terms of p, it's the value minus the mean over the standard deviation. So in this case, 0.875 minus our mean, which is 0.92, divided by our standard deviation of 0.0214. And we kind of saw where it was on the graph. So minus our mean of 0.92 over our standard deviation of 0.0214. Let's see what that equals. 0.875 minus 0.92, enter. It should be negative because it's on the left side of the mean. Divided by 0.0214. Negative 2.10. Standard deviations. So this is another way you could answer this question, and that's kind of what we saw on our graph. Boy, I keep doing that. It was right here. We also have the graph right here. 0.875 would be right in here somewhere. So that's going to be 1, 2, and a little more standard deviations to the left. Okay, so we could say that would be more than 2 standard deviations, I'm going to have to abbreviate, from the mean. So that's another way to show it's unusual, either a small probability or a high z-score. Okay, so use this information, use these examples to try out the homework, and I will see you soon.